Next point, having considered about the various and talked about the various characteristics and the model of a diode, we'll move into its biasing. Here I would like to tell you some basic points considering that you have already know about the PN junction. If you don't know about the PN junction much, then kindly refer to my slide on electronics devices. Where I have briefly talked about the inside mechanism of a PN junction diode, and which will be very helpful in learning about the inside mechanism of the PN junction diode. Now, if you look this in the forward direction, this is actually the internal mechanism of a PN junction diode. It consists of two charge carriers. One is the majority charge carrier and other is the minority charge carrier. If you look at in the p side region, you will see that this region is doped with a p-type semiconductor. A p-type semiconductor we have already talked about. It is a type of semiconductor which have 5 valence electrons, right? No, I think you must be thinking that she's talking wrong, but yeah, I'm wrong in that sense that it does not contain 5 electrons, it contains 3 electrons in its valence shell. Thus it obtained 1 electron from the silicon present in the diode as a majority carrier and turns itself into a negative acceptor ion or into a negative ion or an acceptor ion, and other as a positive ion. So it is the majority charge carriers are the positive ions with negative acceptors. On the other hand, in the N-type region, it is mostly the opposite of the P-type region. Here we doped it with a with electrons that have 5 valence shell, 5 valence electrons in its valence shell. Thus, they donate one electron, making themselves as donor ions and other as the negative. So they are positive charge and the other is negative charge. So you will find that the negative charge is a majority charge carrier in N-type and the positive charge is a majority charge carrier in the P. In the forward direction, we'll see that the majority carriers move from the plus side of the region to the minus side, and in as we have talked earlier that in forward direction the depletion region shrinks. It doesn't expand but it shrinks, and the potential developed across this depletion region is subtracted from the actual circuit diode region. So this was a major analysis of a PN junction diode. Now moving on, explaining that in forward direction we'll see that the diode is in on condition when the p side of the diode is conducted to the positive terminal and n side of the diode is connected to the negative terminal. The application of the forward bias pressurizes the minority carrier present near the ions to merge with the ions and reduces the width of the depletion region. Both the ions merge, both the plus and the minus merge to form a permanent depletion region, a reduced depletion region. Now we have already talked about the diode current, that diode current is equals to I of S e to the power Vt minus Vt, whereas the saturation, where Is is the reverse saturation current. For appreciable current I in the forward direction can be approximated by the exponential relation I is equals to Is e to the power V slash Vt. In the logarithmic form, we can say that V is equals to Vt natural log of I over I. Now, if we have two different diodes with the two different diode current and two different potentials, then we can calculate the difference between the two diode voltage V1 minus V2 or V2 minus V1 by this formula, which is 2.3 Vt log of, not natural log, but then log to the base 10 logarithmic log is equal into I2 by I1. Okay. At a given diode current, the voltage drop across the diode decreases by approximately. The voltage drop across diode decreases. Remember, it's the voltage drop, not the diode current. If we get confused oftentimes because the diode current or the reverse saturation current, it doubles for every 10-degree rise in temperature, but the diode voltage decreases for every 2 millivolt for 1 degree, for every 1 degree Celsius change. Okay, it decreases. Remember that. Now